Hi, my name's Mike Jones. I'm from Oxford University in the UK, and so I'm going to be giving a couple of lectures this week on some different aspects of radio astronomy. So we're going to start with just a very general overview of radio astronomy, what it is, what kinds of things we look at in the universe, and what kind of instruments we use to do that. So if we look at the sky using ordinary light, optical light, then this is what we see. This is the night sky in the optical. Obviously, a very sort of deep mosaic image taken from various telescopes around the world. And what you can see here is very much dominated by starlight. You can see lots of individual stars. You can see stars so densely packed that they look like continuous light. And then obviously we can see the absence of light from stars where there's dust in the way, and some of the reddish glow you can see is actually genuine diffuse emission from hydrogen. But this is the sky that we're familiar with, that you look up and see on a dark night. This is an image of the radio sky, or it's one image of the radio sky. And the first thing you can see is it looks completely different to the optical sky. And in fact, the one thing that you really don't see very much of in the radio, few exceptions, is stars. So in this image, which was made by the Planck satellites over a wide range of radio wavelengths, mostly what we're seeing here is emission from interstellar medium in our own galaxy via a variety of emission mechanisms, which we'll talk about in a moment. The Planck satellite was a very small telescope in orbit, designed to look mostly at the cosmic microwave background. And because it's a small telescope, it sees mostly this diffuse emission very well. If you look at the sky in the radio, but with a much larger radio telescope, and so this is a compilation made from several very large radio telescopes in the northern and southern hemispheres, what you see is completely different again. So now we don't really see the broad diffuse emission from our own galaxy. That's resolved out. What we see instead is a huge number of compact unresolved sources, and the sky is full of these sources. And you can see the galactic plane faintly through the center of the image. Those are compact sources within our own galaxy. But apart from that, you can see that the sources are spread pretty much evenly over the whole sky. I mean, the gaps and the changes in color are just due to the coverage of the different telescopes and the sensitivities being slightly different in different areas. But fundamentally, the sources are distributed completely randomly over the whole sky. And this is telling us that we are looking way outside our own galaxy. And here we're actually seeing sources right across the universe. So to summarize that, the optical versus the radio sky are very different. The optical sky, say, is mostly stars. That means we're mostly looking at thermal emission. So we're actually looking at objects that are emitting because they're hot, and they're the temperature stars, which are thousands of degrees. This means also that the brightest objects are mostly nearby. So when you look at the sky, even the stars that you see that are in our own galaxy are mostly very close in our own galaxy. You don't even see very far away within our own galaxy. So this is pretty much nearby on the scale of the universe. This also means that very distant objects are very faint. And so, I mean, it's pretty much the rule that in optical astronomy, that the faintest objects are the furthest away, and the furthest objects are faint. This actually makes studying the universe as a whole in the optical quite difficult. In the radio sky, however, so you say we see extended emission over much of the sky. We see a lot of compact objects as well. These are mostly radio galaxies. Mostly the emission that we see is non-thermal, and the brightness temperature, we'll talk about what that means actually in the next lecture, are huge values, very, not correspond to any physical temperature, but radio objects can be exceedingly bright, which is why they can be seen right across the universe. And in some senses, cosmology is easy in the radio because we can see, some of the brightest objects in the sky are actually most of the way across the universe. So what makes radio astronomy radio as opposed to all the other branches of astronomy? So here's the electromagnetic spectrum. The optical, the visible is just a small chunk, and the radio occupies this region of the low frequency, long wavelength part of the spectrum. And there's a physical reason behind why it's radio, and we'll talk about this again a little bit more in a later lecture. But if you think about the Planck radiation curve that describes the radiation from a black body, a radiating object, here's the radiation curves for a set of objects, basically spanning the temperatures of everything you're likely to find in the universe, from the temperature of the microwave background up to the temperature of X-ray emitting gas. You can see that the shape of the curve has these two parts. There's a part which goes as frequency squared, which is the radiation you expect from a classical oscillator. And then there's essentially a quantum correction to this when the number of photons involved starts to get small and you start to notice the fact that radiation is actually quantized. And the thing about radio, it's basically the part of the spectrum where you are always in the classical regime. So you're always thinking of radiation as being essentially an electric field and not individual photons. So there is no lower frequency cutoff to radio astronomy. It is DC to around about 100 gigahertz. But in practical terms, the ionosphere of the Earth prevents us from seeing frequencies below about 10 megahertz. But that's a 10,000 to 1 frequency range, compared to less than 2 to 1 frequency range in optical. And that means that in radio astronomy, we have a huge variety of different kinds of telescopes that work well in various subsets of that frequency range. And as I said, we're talking about a region here where the photon energies, if you were thinking of photons, are tiny fractions of an electron volt, much more than the energies involved in almost all chemical and physical processes. And so that's why we don't really think about photons in terms of radio astronomy. So it's worth talking a bit about the different emission mechanisms which emit radio waves that we observe with telescopes from different objects in the universe, because again, it's quite different from what's observed in the optical, and it's quite different from the world we see with our eyes, which is mostly illuminated by sunlight, which is essentially thermal radiation. So the different emission mechanisms we're going to talk about are synchrotron radiation, free emission, line emission, and then a little about what's called anomalous microwave emission. So synchrotron emission first. That's probably the most important mechanism in radio astronomy. It's what most of the radio sources, the compact sources that you see in the radio sky, it's how they emit most of their energy. And this comes from ultra-relativistic electrons, so electrons whose energy is very much greater than their rest mass. Electrons acquire these very high energies in supernovae and near black holes. There are mechanisms that can accelerate a small fraction of the electrons in these objects up to very, very high energies. And there are magnetic fields throughout the universe. And when an electron travels through a magnetic field, it spirals around the magnetic field, and the acceleration of that spiral motion causes the electron to emit radiation. Now, an electron will emit radiation at whatever speed it's going, but the thing that makes synchrotron emission particular is because the electrons are highly relativistic. That means that the emission that they produce does not spread out in all directions from the electron, but is beamed very tightly in the direction that the electron is moving. So that means if you imagine watching an electron spiraling around a magnetic field, you won't see it emitting radiation unless it happens to be coming almost directly towards you, because the energy is beamed forwards. And then you get a very, very brief, essentially a click of radiation as the electron, as the beam, relatively beamed radiation sweeps past you, and then it disappears again. And so what you see in synchrotron emission is the sum of all these millions of clicks of individual electrons sweeping their relativistically boosted beam in your line of sight. And that assemblage of very, very brief sort of clicks of radiation gives you a very, very smooth spectrum of radiation, which spreads over many decades of frequency. And so when you look at the spectra of these typical extragalactic radio sources, you have these very smooth spectra over many decades in frequency. And in fact, most of the features that you see, like you can see, this one is it's got some little kinks in it. That's actually due to the fact that there are different physical parts of the object with slightly different conditions, and therefore their own spectrum is slightly different. And you're just seeing those spectra add up. The spectrum that's produced by any particular bit of the source that has a particular field strength and electron population is very, very uniform. So when you look at the sky, so you see a lot of objects radiating in synchrotron emission. At the bottom right here, we have a typical giant radio galaxy, where we have a galaxy with a black hole, supermassive black hole in the center, material falling in, being accelerated at the black hole and sent out in these jets, which then impinge onto the surrounding gas and create these great lobes. So all this radiation that we're seeing here is synchrotron, and where the jet hits the surrounding medium and compresses, the magnetic field is compressed as well, the density goes up, the magnetic field goes up, and the synchrotron strength goes up accordingly, and we see these bright lobes. We do also see synchrotron from our own galaxy. This is a map from one of our experiments in Oxford, CBAS, showing the northern sky and most at low resolution. And here you can see these big sweeping structures are synchrotron radiation from, well, this one's from a relatively nearby old supernova remnant. And you do actually see, you can see synchrotron radiation in the optical. So this is the Crab Nebula on the left, a recent supernova remnant, only 1,000 or so years old. And you can see that this is a radio image, and this is an optical image. And you can see that they really look very, very similar. You can see individual features, filaments that are exactly the same in the radio and the optical. And this is actually synchrotron radiation extending all the way into the optical. It's basically, this thing is so bright that even though synchrotron radiation tends to drop off quite quickly as you go up in frequency, there's still enough to see by the time you get all the way to the optical. So our next kind of radio emission is what's called free emission, sometimes known by its German name Bremsstrahlung, which means braking radiation. And this is what you get when you have ionized gas, for example, around hot, bright stars. And electrons are moving around, and every so often they will encounter a positive ion, and the electron basically bounces off the positive ion. Its course is sharply deflected. It turns out when you do the sums, but electron-electron collisions and ion-ion collisions produce very, very little radiation. It's the fact that the electrons are light and the ions are heavy, and the electrons are the things which are doing the moving. Means that it's the electrons which give off most of the energy. This also gives a very smooth radio spectrum. At lower frequencies, it's actually possible for the radiation to be absorbed by the same population of electrons that's emitting it. And so you end up seeing something which looks very much like a thermal hot object. And then at higher frequencies, where the electron are effectively transparent, you have this very flat slope with frequency. And so you see a lot of this in our own galaxy, particularly in interesting bits of the galaxy where there's star formation going on, or recent star formation, and lots of hot stars and lots of ionized gas. And so here's, again, a comparison between the radio and the optical. So in this optical image on the right, you can see a nice chunk of sky near the plane of the Milky Way. This is actually Orion down here. We've got the Orion Nebula in the center. This is Lambda Orionis, another star-forming region. And what you can see in the optical image is where you've got this red gas, that's hydrogen alpha emission. So that's telling you that there's ionized gas. And then in this radio 3-color image, you can see, so in these particular colors, free emission comes out as this kind of cyan color. And again, you can see exactly the same structures. This is Barnard's loop here around Orion. And you can see that where you can see ionized gas in the optical, you can see the same ionized gas in the radio. Right, then there are many kinds of line emission, where processes that produce radio waves at very specific frequencies. Now, we said most energies involved in atomic processes, molecular bonds, that kind of thing, are actually very much greater than radio energy. They're more like optical energy. But there are some low energy changes of quantum state which result, and this is one of the things where you do actually have to think about the radio as being emitted as photons, because you've got atoms or molecules changing their quantum state and giving up a little bit of energy as a radio photon. So the two sort of most important things are the H1 line, which we'll talk about in a moment, and then molecular rotational transitions, where you've got asymmetric molecules changing essentially their rotational speed. So H1 is a particular very important line emitting process in radio astronomy, and because it involves hydrogen, which is atomic hydrogen, which is the most abundant constituent of the universe in terms of ordinary matter. And basically this is when you look at the spin of the proton and the electron in a hydrogen atom, those spins can either be parallel or anti-parallel. And the energy difference between the two states corresponds to a photon of this frequency, which you can see is extremely precise. And because there is so much hydrogen in the universe, even though this is a very, very weak transition, so a typical hydrogen atom can literally wait millions of years between flipping from one state to another, but there's so much hydrogen that this is actually quite a strong signal wherever you've got concentrations of matter in the universe. And it allows us to precisely trace the velocity of the gas, either due to the intrinsic movement within a galaxy, say, or due to the cosmological redshift due to the expansion of the universe. It's one of the key tools which was used to essentially establish the population statistics of galaxies, because the more massive a galaxy, the faster it spins, and you can measure that spin by looking at the Doppler shift of the H1 line. There's a tight correlation, the Tully-Fisher relationship between the width of the H1 line seen from a galaxy and its mass. And then we can also use hydrogen to trace really the evolution of the universe, because it's emitted throughout time, and as you're looking further back in time in the cosmic history of the universe, the H1 line is redshifted, and so the frequency that it's redshifted to tells you exactly how far back you're looking. And this is one of the big motivations for building the SKA, amongst other big projects. So if you look at our galaxy, look at the velocities. Here's an all sky, very beautiful all sky H1 map where the colors are encoding the velocity, and you can see the systematic change across our galaxy due to the galaxy's spin. This down here is the Magellanite clouds, which have their own completely separate velocity. And on the right here, this is actually a plot made by one of our students here in Oxford, using one of our teaching telescopes. And this is the line profile showing the brightness as a function of velocity, as measured with H1, as you go around the galactic plane, from all the bits of the galactic plane that are visible from here. And you can see this nice systematic shift in the velocities as we're looking at around the galactic plane. When you look at other galaxies, it's obviously a bit easier to see this effect from the outside rather than being inside the galaxy looking out. And there are lots of very nice observations have been made. Here's a typical spiral galaxy, and this is obviously the optical. This is the radio image. These are at the same scale, so you can see that the hydrogen goes out very, very much further than the obvious collection of stars. And you can make similarly beautiful pictures of many, many external galaxies. And then this is what the integrated spectrum of an external galaxy looks like. And you can see here, this is the fact that you're basically looking at a spinning disk. So the edge on one side is traveling towards you as fast as anything can be in that galaxy, and then the opposite edge is traveling away from you at the same speed, and then there's rather less material traveling at intermediate speeds. And so this spread in velocities tells you essentially exactly how fast this galaxy is rotating. And then, as I said, a big goal, this is mostly a goal for the future, but in principle, you can explore the entire history of the agglomeration of matter in the universe by looking at the redshifted H1 line. And so people have done simulations like this one showing at some early stage in the universe at high redshift, you've got a patchwork of red, which is the atomic hydrogen, which emits the H1 line. And then the blue in between is the ionized hydrogen that's been ionized because stars and galaxies have turned on and started creating photons that ionize hydrogen. And so with telescopes like the SKA, SK low particularly, you can imagine observing this structure and distinguishing between the neutral hydrogen and the ionized hydrogen, and just seeing if it really does have this structure, which is what we see in these simulations. A couple of years ago, there was a claimed detection of essentially the absorption of background light by the hydrogen in the galaxy at around the time where most of this, what's called reionization, when the first stars in the galaxy switch on and the universe shifts from being mostly neutral to mostly ionized. That was claimed a couple of years ago, and we're still waiting to see if that's really confirmed. And so this is a very much active area of observation and telescope building at the moment. So then, I mean, other molecules and atoms produce radio lines. So common molecules like water, oxygen, carbon monoxide have either rotational or vibrational states whose energies correspond to radio frequencies, and these are very important for tracing structure of matter in the universe. Carbon monoxide is particularly important because it's essentially the next most abundant thing after hydrogen, but the hydrogen molecule is symmetric and actually doesn't have many of these rotational transitions, because carbon monoxide is asymmetric. Basically, there are more distinct angular momentum states, which means that it produces lines which can be used to trace molecular gas. Sometimes you can, in particular special conditions, particularly the atmospheres of some stars, you can get a state where you've got more molecules in a higher energy state than a lower energy state. It's called the population inversion, and that's what happens in a laser. And you can get a state where the radiation emitted by one molecule triggers another molecule which is in an excited state to drop to the lower state. You get stimulated emission, you get a cascade of photons, each tripping molecules into their lower state, and this makes very, very bright radiation. That's called masers, microwave equivalent of a laser. And you can see here an image of behind this disk, there's a star, and these are essentially blobs in the atmosphere of the star that are producing this very intense maser radiation. So there's also a thing which is on the upper edge of the frequency range of radio. We start to see a kind of thermal emission. So there's obviously a lot of dust in our galaxy, in the Milky Way, and it emits a lot of radiation in the sort of 100 gigahertz and upwards. And this is almost thermal radiation. It's thermal radiation, but where the dust grains that are radiating are actually smaller than the wavelength of the radiation that they're emitting. So that means they don't emit very efficiently. But as you go up in frequency, the radiation gets closer and closer to the size of the grain, and the efficiency of emission goes up very rapidly. And so you get this very, very steep rise in brightness in the few hundred gigahertz range as the wavelength starts to match the size of the dust grains more accurately. And so this is then therefore a good way of seeing dust, and say in the sort of 100 gigahertz range. So the ALMA telescope has produced some of these beautiful images of the dust disks in solar systems which are in the process of formation, where all this dust is beginning to clump together and form planets. You can start to see the gaps in the dust where the planets are going to form The gaps are because the dust is accreting into larger and larger objects, which will eventually form planets. And actually, one of the things which the SKA will do is follow that that process up into the larger objects. So rather than seeing the dust, seeing the kind of pebble rock-sized objects, which are centimeters in size, so the wavelengths which will be observed with the SKA. Another emission mechanism discovered relatively recently, and it wasn't really predicted. That was maybe a paper in the 1950s, I think, which suggested this, but everybody had forgotten about it when the time it was actually discovered. And this was seen as essentially a bump in the radio spectrum in regions where there's lots of dust, but this is very, very far away in frequency from the normal dust emissions we were just talking about. This is frequencies around 20 or 30 gigahertz. And what we think now, although it's still not probably 100% sure, is that this is a new emission mechanism where you've got these same dust grains, and they're little elongated grains, and they're spinning. They're almost like giant molecules, these things. They're really quite tiny. And it's the rotational transitions of these quite sort of big dust grains, which is giving rise to a very finely spaced spectrum of line emission, which is producing this bump, which we see, say, around a few tens of gigahertz. It was discovered by people trying to study the microwave background, and it's a problem for people trying to study the microwave background, because it's another component of stuff that isn't the microwave background which gets in the way of trying to observe the microwave background. So finally, the microwave background itself is an important radio source. So there are not many things we observe in the radio which are thermal radio, but this thermal emission, but the CMB definitely is. It's very, very thermal. This plot here is the famous spectrum of the microwave background obtained from the FIRAS instrument on the Kobe satellite, and this is a plot of the best fitting blackbody spectrum, and these error bars have been increased in size by 400 times so that you can actually see them. So you can see that the spectrum fits the curve of a black body extremely well. And the CMB is actually the brightest thing in the universe. If you look at the average brightness of the sky over a wide range of frequencies, so all the way from radio all the way up to gamma rays, you can see, so this is here the cosmic optical background. So that's basically all the starlight in the universe added together, and then infrared sources, X-ray sources. The microwave background sticks up, an order of magnitude above everything else. It is the most important source of photons in the universe. Okay, so that's what we're looking at. We'll talk quickly now about how we look at these radio waves. So radio telescopes obviously start off with an antenna. There's the classic radio telescope view, which is the dish antenna of various sorts, where you have a metal parabolic reflector focusing the radiation to some kind of focus. But there are also what are called horn antennas, which may have a reflector on them, which are essentially flared waveguides. And you can also have generically called wire antennas, so things like dipoles, Yagis, basically things which look like television aerials, and those are typically used at low frequency. But in all cases, you can basically say these are something which has an ability to absorb or collect radio waves, which they do over some effective area, which tells you basically how good that antenna is at collecting radio waves. And so the two sort of first fundamental things that you think about with any kind of telescope are its sensitivity and resolution. Now, sensitivity depends on collecting area. The amount of power that you can receive is just proportional to the brightness of the thing that you're looking at, or rather, sort of the flux density of the thing that you're looking at. We'll talk about the difference between brightness and flux density later. And that's collected over some area. The resolution, whether you're able to resolve fine detail in an antenna, depends on the size of the antenna as well. Now, for a single circular antenna, obviously these two things are tightly linked. So the area is given by the size. It's the area of the circle times some efficiency. But it's worth remembering as well, but that's only true for single dish telescopes. So if you're thinking about an interferometer, for example, the D that's relevant to an interferometer is the distance between the antennas, which can be very large. But the A that's relevant is the total area of the individual antennas added up. And so those can be very, very different if your interferometer consists of relatively small antennas that are relatively far apart. So once the radiation has got into your antenna, it's essentially become a voltage on a piece of wire. And now we're now into the realm of electronics because we have to deal with that voltage and amplify it and detect it. So the first thing you have to do is amplify the signal. You want to do that whilst adding as little extra noise as possible, because the signals are exceedingly small. So if you think about the sort of typical unit we use to measure brightness of, flux density of radio sources, 1 Jansky is 10 to the minus 26 watts per square meter per hertz. So that means that if you have let's say a 26 meter telescope and you're observing over 500 megahertz of bandwidth, you've got about 10 to the minus 15 watts is the actual power from the source that's entering your telescope. It's obviously a very, very small number. So you have to make specialized amplifiers to amplify that signal up to a level that you can see. Now, there's going to be a whole lecture on receiver design or later, so we won't go into this detail now, but to say that there is a whole business of designing, putting together the various bits of electronics that are needed to pick up and detect these signals. We quite often have to cool those down to temperatures of a few degrees above absolute zero to reduce the noise. And so receiver design is a combination of electronics, microwave electronics, and cryogenic and vacuum engineering to actually get this whole thing cold. This is unusually a receiver actually in the telescope in place, but with all the outer casing removed, so you can see all these electronics components inside, which would normally be well closed up and cooled down. And again, not to go through this in any detail, but this is these are block diagrams of a couple of different of receivers, and just showing you the kind of processing which goes on and the kind of components that we'll need in order to produce signals that we can then detect and do something with. So just look at a few telescopes. So these are some single dish telescopes, just to sort of see the kind of range of things that we're looking at. And I've scaled these all these photographs. These are pretty much to scale. So this is the 26 meter telescope at Hartwiestuk. This is the 76 meter telescope at Jodrell Bank. This is the 100 meter telescope at Green Bank in the US. This is an old photograph of the 300 meter antenna at Arecibo, now sadly defunct. And this is the currently largest single aperture telescope in the world, the 500-meter spherical telescope FAST in China. So single dishes are not the only way of building a telescope. So to get resolution, you need to increase the size of your telescope, and at 500 meters is really a pretty extreme feat of engineering for a single telescope. But that doesn't actually give you a very good resolution because radio wavelengths are so long. You need many, many more wavelengths to get even to approach the resolution of the human eye. So you want a way of increasing the resolution without increasing the size of the individual antennas. And so that's what interferometers do. So this is the very large array in a fairly compact configuration. And so here you can see you've got now relatively small antennas compared to the overall size. Each pair of those antennas, if you take the spacing between every pair of that set and plot it, you get a picture like this. And so this shows you all the different spacings and orientations that you get from that array. And every one of those spacings essentially gives you one component of the Fourier transform of the sky. And you can then take the information from each of those baselines and invert it to produce an image. I'll just very briefly, as we're talking about interferometers. Interferometers necessarily bring up the subject of Fourier transforms, but you really can't get very far in radio astronomy without thinking about Fourier transforms. So Fourier transforms relate pairs of variables, for example, frequency and time, or it can be angle and baseline. Going from one Fourier domain to another is essentially a very different way of looking at the same information. And there are various theorems which tell you how, for example, the time extent of a piece of data tells you about the frequency content. Mathematical operations like multiplication and convolution have their converse operations in the opposite Fourier transform domain. And there are many things in radio astronomy where you want to think about two things which are Fourier transform pairs of each other. For example, the beam of an antenna and its illumination function, that is the strength of the electric field across the face of the antenna. The frequency spectrum of a signal and the autocorrelation of that same signal in the time domain, the baseline coverage of an interferometer and the response of the interferometer to a point source. There are lots of these things, and so really you need to get your head around Fourier transforms because they come up all the time. And it's like this little cartoon which kind of illustrates one of the cool points about interferometry, whilst slightly confusing it. So if you replace dogs with antennas, then this is essentially what interferometry does. You place two small antennas a large distance apart. They can function like a single giant antenna. And essentially, the caption to this cartoon is actually a very important statement about interferometers, but disguised into talking about dogs, because it is important to remember that although the effective size of the telescope can be arbitrarily large, it's not any more sensitive than the original two antennas. So the sensitivity depends on the actual amount of collecting area you've got, whereas the resolution depends on how far apart you put those antennas. And there are lots of interferometers out there in the world. Here are a few of them. As you say, lots of different designs mostly different because of the different frequency range that you're trying to cover, all the way from tens of megahertz and here for LOFAR up to hundreds of gigahertz for ALMA. And it's worth just thinking about how the resolutions that you get with different telescopes relate to maybe the resolution that you're more familiar with. So the human eye has a resolution of a few arc minutes. You can get that with, say, a Greenbank class telescope operating in the microwave. Going up to a small telescope, that's the equivalent of a big array like the VLA, a big optical telescope, or a diffraction limited, fairly big optical telescope like the Hubble telescope, is then comparable in resolution to international VLBI networks or global VLBI networks. So that brings us on to VLBI, which again, just mention it's a special kind of interferometry where you don't actually combine the signals in real time, but you can essentially you record the signals at each individual antenna, originally on tape. These days you do it on disk, and then at your leisure you can bring those disks together and combine the signals from the antennas and get the signals you get that you would have got if you'd done it in real time. And so this is a way of connecting telescopes that are essentially so far apart that there's no physical way of connecting them together in real time. And finally, one important and very practical aspect of radio astronomy is you can essentially turn radio astronomy upside down. Normally, certainly in interferometry, what you're saying is you have a set of antennas that you know where they are, and you're looking at things in the sky, and you want to work out what it is that you're looking at in the sky. There's the application of radio astronomy in geodesy is to say, I'll just look at a few objects in the sky that I know very, very well what they are. They are bright point sources that are a very long way away. And then you use that to find out where your antennas are. And then it turns out that you can actually measure the position of your antennas very, very accurately. And then you can actually do things like you can measure the rotation of the Earth at a very high level of accuracy. You can see all the wobbles and shifts in the position of the Earth's axis. And you can track continental motions, continental drift. You can actually see antennas on different continents moving relative to each other. And then occasionally, the slow movement turns into a big jump. So this is the distance between an antenna in South Africa and in Asia. And this, you can see the slow continental drift going on. And this is the March 2011 earthquake, which caused the tsunami in Japan. And you can see that earthquake was a sudden jump of several meters in that baseline. Okay, so that's the end of the introduction, and if there's still time, we'll move on to have some questions. Thanks very much.